Thank you very much. I'm so pleased to be here again, and actually not in this new building. I missed the opportunity last year and when your new building built, so I hope I was there last year. But nevertheless, I made this year now. And also especially thank OSA and SPIE chapters for your kind invitation. Congratulations for your wonderful meeting here now. So I'm really impressed about other speakers which you invite coming here now. Outstanding. Well, I'd like to really ask one question for all of you here now. How many of you are students? Please raise your hand. Okay, all right, good. This is one I'd like to know. How many of you are physics students? Please raise your hand. Wow, okay, thank you very much. So should I talk more about the physics? No. Yeah. Okay. Actually, on purpose here now, I like to talk about imaging, talk about terahertz imaging. And hopefully at the end of my talk here now, I will cover a few things about the potential terahertz quantum imaging, which I'm working on that. And also at the end of my talk here now, or maybe my slides, I'd like to make a new announcement about our group activity, which I spent more than 10 years. And most of us believe is not possible, but we made it possible. So today, actually, I'd like to really use this opportunity here to talk about imaging beyond the light. This is actually a title, is not a title which I select. It's a title recommended by your chapter. So all of you know we have OSA 100 years anniversary at Rochester. Rochester is the birthplace of American modern optics and also birthplace of OSA, Optics Society. We don't call of America now, even we call OSA, but we call Optics Society because it's international society now. I like this one especially because it's a fellow pen, bright. I also have SPIE fellow, is red, not as visible as this white one. I should be a little bit careful because I know there's video. I don't want to be pissed off by other society. Now, I like to introduce you one of my students sit next to me. His name is Jingo Liu. It's a very interesting story I share always with my student, and also, of course, with a lot of students here now. Jingo was my PhD student in my group. He is a student, or he was a student I almost want to fire. He's come to work in the morning 10 o'clock and leave at 3 o'clock or 4 o'clock. Weekend never come back. When I'm on travel, like today I'm travel here, is on his vacation. After 3 or 4 years, in my group, 3 years, I called him to my group, my office. I said, Jingo, I no longer can supervise you anymore. I don't see you. Find another advisor, right? So he said, Professor Zhang, I really, really want to work with you. I enjoy your project, you know. Could you give me probation? Give me 3 months. I thought I gave you 3 years already. 3 months is okay. Give you 3 months. In 3 months, as a graduate student, he made one of his most important decisions in his life. We have so many students here now. Tell me, what could be your most important decision can make in 3 months? What? I didn't hear it. Anything. The most important decision he made, he found a stable girlfriend. So I realized actually in the past 3 years, he was chasing a girl and changing the girlfriend, and he cannot concentrate. So he found a problem. The problem is he needs a stable girlfriend. So once he found it, he changed his life. He started to work 7 o'clock in the morning and left 11 o'clock, sometimes overnight. And look, he published 16 papers. And 13 papers, he's the first author. 10 papers in 1 year. How can you do it? Must be fun, stable girlfriend. So all this paper here, Nature Photonics, Physics Review Letter, Optics, Express, Optics Letters, Applied Optics, Physics Review B, all these top journals, he's first author. So after he achieved his PhD, he got multiple offers. He came to my office again. He said, Professor Zhang, I have demonstrated my ability to do good in science. Now I'm trying to demonstrate I can make money. I said, wow. He worked for Bloomberg. Now he's actually make $1 million a year, which is much, much more than everyone made. Another amazing here now, because he's an outstanding scientist, he said, Professor Zhang, I want to stay in the US to pursue my dream. And he applied green card. The day he submitted his application to get green card, the day he got green card, 23 days. That's a record. Most of people takes over a year to get a green card. So what I learned from my student here now, why I share the story with you here now? We all know students are the best products of our faculty, right? As a faculty, what I'm proud of, not by number of papers, not by the patents we have, not by our own prize we got, it's by production of the best students we can have. I feel bad Jingo is not staying in science, but I'm happy actually we have a better people to help us to manage our wealth, to manage your money or our money. So now he is doing very well in the financial case now. Now let's back to the story here now about imaging story here now. I have been working on terahertz for a number of years, one of the earlier people in this field. But until 2003, I suddenly realized the terahertz technology not only for curiosity, but can be used for real life. We lost Space Shuttle Columbia. 7 astronauts was dead after the space shuttle returned back. So believe there was a defects here now. Defects between the space shuttle and also external fuel tank. So when the shuttle left here now, this part called thermal insulation, a very big, very light, they hit on the shuttle's wing at the speed of the sound. So it can cause a big hole. When the shuttle returned back to the Earth, the hot plasma into the shuttle killed all 7 astronauts. Then I was really asked, how can we use a terahertz technology to find the defects or delamination for this material? So one of the earlier systems which we built, we have some physics students here now, we have a terahertz source we call GaN diode, and then we send out this terahertz wave, treat as optical beam, and focus into the sample, either in transmission or reflection geometry. Then we move the sample or we move the imaging system. Then we are able to rebuild the system. So these two small things, one is 9 pounds, one is 6 pounds, they are the device my PhD students built in the lab. Not very pretty because we are physics students, we're not engineering students. So, but we can build concept. We know how to build it. We don't know how to build it beautifully. So this system here can radiate terahertz wave and detect terahertz wave by using these boxes here. 2 of my students, they are photo in the Nature, which is, let's see, 14 years ago. They send a terahertz wave down, and this actually is a thermal insulation for space shuttle. And they really scan the material here, or scan the system here, to build the imaging, terahertz wave imaging. So this also actually is a company, major company in US called Lockheed Martin. Lockheed Martin actually, they build space shuttle system. So I'm not going to read this entire request. The request says, we are investigating and like to find, you have any idea how terahertz may be applied to the thermal insulation issue here now. We are interested in seeing a void with the form itself and delaminations between foam and aluminum substrate. Finding some way to do it. This was request. I call it present challenge. Rather than just a professor here write a paper, publish a paper, you don't care. What is a real application? This perhaps represents a great challenge for us. Are we able to use the technology which we develop to find such defects? So in a very short time, US government, NASA, create a 4 major activity. So one group doing a called microwave imaging. My group is terahertz wave imaging. There was another group called scatter X-ray, like a backscatter X-ray, also called laser shiography imaging. Laser shiography is you put your sample into a big chamber, you take a laser hologram, then you vacuum the chamber, you retake the hologram to see the deformation. That's called a laser shiography. My team is terahertz imaging. Now, if you look for the blue area here now, represent the frequency. Here's a microwave, here's a visible beam. So terahertz wave is between the far infrared and the millimeter wave. So this is the range which we are working here now. So then I work very closely with NASA. NASA brought sample here, huge sample. Okay, they are size typical by meter size. And we are looking for defects within the thermal insulation. Your eye cannot see it. It's not transparent for optical beam. So you have to use some kind of invisible beam here now. In this case, we use a 0.2 terahertz. We imaging this meter size thermal insulation. This can prevent heat. We found most of the artificial built-in defects. We found 49 out of 57 defects. We didn't find all of them. Reason because terahertz wave cannot go through the metal, and the terahertz wave will be absorbed by the water as well, severely absorbed by water. But we find quite a lot of defects here now. So then immediately I received a report from NASA. NASA said finding 49 out of 57 was impressive. I wasn't thought impressive. I thought we miss even one is not impressive. But they call it impressive. The reason is because the false alarm rate is very good. So NASA follow our step. They also built a system. They found 14 out of 19. It ranked with the best of the method test. Remember the 4 method, and this ranked the best of the method. And the key issue is no false call rate is very, very important for NASA's operation. So even I did not find all of them, some of them hiding under the metal, I'm not able to see it. But relatively comparison here now, it works very well. Therefore, return to flight and beyond. This is a NASA report. Backscatter X-ray and the terahertz imaging are 2 alternative methods for NASA use now. So we are so pleased. We are able to help our member here. So this is actually a system which I built, nearly like hand built. Scanning system can scan X, Y 1 meter, and I built this one here, and this one run at 0.75 meter per second. The sample we have here, so we have to move because sample can be very big, can be as big as this building. So we have to really move our sensor detector. We are able to measure everything inside here now in the reflection geometry. So we built a couple of systems. We sent to a company and also government in Florida. They are using our system for every space shuttle before they return. Another pretty work here is I was at RPI, as Aruna mentioned here. I was at Rensselaer. So NASA put a Rensselaer continual wave terahertz method on a fast track. Also get a space certification. That is a very big honor for university faculty here now. Now this is actually a warm-up here now. So how we use terahertz wave imaging. And our group is not only a group to do this. There are many other groups. This is one group actually from France. And you can see this actually is a dome. And they put an imaging system here now. They are able to imaging something inside of the building. Because a terahertz wave is kind of transparent here now. For our clothes, everyone have privacy or one other reason you wear clothes. And so we have to keep our privacy. But I was asked actually 3 months ago, US Army asked me to develop a terahertz goggle for them. So what happened here? Once you wear terahertz goggle, we are naked. I don't know if I don't do it or not, but it goes through many of our clothes. So once a terahertz goggle is available, I'm pretty sure the clothing company here will have to build a metal wire inside of your clothes to protect your privacy. Well, I'm not too sure how far we can go there. But there are a person here inside of this dome here now. So you should be able to see people inside of the dome. Another company in UK called Kinetic. So in more than 10 years, 15 years ago, they have their paper in science. So a person here outside, I have a piece of paper, and terahertz wave can see through the paper. So you can see there was a knife here, even have a gun inside the pocket. In one of the first slides which I show you, I was in Miami, and I sending a terahertz image of myself for 18 meters away. And if I have a pocket, like a screwdriver in my pocket here, you'll be able to see 18 meters away. How's the resolution? Resolution can be greatly improved. This resolution is pretty bad, okay? This resolution, a very poor resolution. But you don't see close, basically, you see everything here now, right? And the resolution can be 10 times better. So once the resolution is getting better here now, then we may have some issue here for privacy issue. And this is on purpose a low resolution. At US airport, you go through this millimeter wave. They ask your hand to rise up here and have you rotate, or maybe the machine rotate you now. That one can have a very high resolution. But now by US government policy, on purpose, we're not able to show the better resolution. Actually, I serve as National Academy of Science member to evaluate this kind of system. There are 740 systems in US airport, 740 systems. And our job is to measure the power of this imaging here, make sure women, especially pregnant women and the kids, are safe doing such kind of operation. The manufacturer companies say, safe, 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 for sure. But our job serve as an independent consultant, provide scientific number to make sure this is safe. This is 35 gigahertz. It's not even terahertz yet, right? So with terahertz, we call 100 gigahertz to a 10 terahertz, or 300 gigahertz to 10 terahertz. Here's only a 37 gigahertz. But for the dome, before I show you, and they are able to see people inside already. So basically, if this building wall is not metal, only glass or this curtain, outside people is able to see our body fairly well. Because this is a frequency, can go through the paper, plastic, board, and some others. Can go to thin layer of ceramic, but a white ceramic or with a metal ceramic, it will block a terahertz wave as well. So far we mentioned about terahertz wave here, we mentioned here how we generate and detect. Since more than half of the students from physics, with a physics background, I only show 2 or 3 slides with very little physics. This one is really a nonlinear optics here now. We use a very short laser pulses, picosecond, femtosecond, very short pulses. We send the laser beam into a nonlinear crystal called electro-optical material. So I will prove very short laser pulses into the material here. It will generate a terahertz wave through a nonlinear process. There's one very famous physics concept called uncertainty principle. Uncertainty principle said the products of time, duration, and the products of the spectrum bandwidth should be greater or bigger than 1. So it's uncertainty relationship. So in another word, if this time laser pulse duration very short, so if this is very short, for this relationship here, you need a spectrum pretty broad. So you need your laser beam is not a single color anymore. Your laser have a pretty broad spectrum from uncertainty principle. The shorter the laser pulse duration, the longer the spectrum. Therefore, different part within the spectrum, they beat each other inside of a nonlinear crystal. And the beating frequency causes dielectric polarization, and it will generate terahertz wave. So the equation which I show here is you generate a terahertz field, not intensity, I'm saying terahertz field, is proportional to the first time derivative of current. This is a virtual current. And the second time derivative of polarization, as well as a second time derivative of your optical beam profile in time domain. So that's, you just accept this is a simple equation which we verify. This is generation. I have to say I don't have a strong credit here in this generation because there were many pioneering people as early as 1970. They already demonstrated to generate a far infrared using picosecond pulses. We are just lucky we have a femtosecond lasers, so we're able to demonstrate. My credit, if there's any here, is come from this slides. This slides actually donate at least $1 million to my university. Okay, and my students every year before Christmas got a check as royalty. So what this pattern comes from? Completely reciprocal of the last slides I mentioned. The last slide is we're sending an optical beam in the crystal, generate a terahertz wave. This slide said we want to use a crystal to measure the terahertz wave. Here's the terahertz wave we like to measure. We synchronize with another optical probe beam together with terahertz wave. So this crystal is isotropic. It's like a glass isotropic, but it is electro-optical material. Electro-optical material. Once they see the terahertz field, we want to measure it, the optical property will change. That's why electro-optic material. So the material become birefringent. It's like a crystal ball. When you see a teller, and the teller, they give you a crystal ball, and they say, your future, blah, blah, blah. How do you know it's a glass ball or crystal ball? Get a piece of hair, put it on white paper, you rotate your ball on the top of the hair. You rotate. If you see two lines, that's crystal ball. If you after you rotate here only one line here, that must be glass. This is the same thing too. When you apply terahertz wave to the material, it becomes birefringent. It's like a crystal ball. If you don't apply terahertz wave, there's no isotropic effects. It's like a glass. So therefore, you are able to use this method to use optical beam to prove the change of terahertz wave. Then you use called push and pull geometry, measure S and the P polarization, which they are orthogonal, and they have equal intensity orthogonal. No terahertz wave, the equal intensity will see two detectors. The current will be canceled by this subtraction. But once the terahertz wave applied to the crystal, applied to the zinc telluride in this particular case, it breaks the balance between S and the P. You have a net current. The net current here gives your terahertz field. This is not intensity. Our eye, your eye, we only can see intensity. We don't see the field. This method see the field. Why is it important to see the field? It will be a coherent measurements. So here's actually 12 figures I show you: chemical, biological, and explosive materials. By sending a terahertz wave, I just show you and measure the transmission or reflection. you take spectrum. Even you take in time domain, but it's coherence measurements, right? You can easily transfer to frequency domain. So all these horizontal axes are terahertz frequency, and the vertical axis are absorption coefficient in wave numbers. Spectroscopy like to use wave numbers, centimeter inverse. So you see there's each of them, they have unique features, and they are different. This is called fingerprint or signatures. By seeing the target compared with your sample, with your reference, you are able to identify what it is. For example, this explosive material, I put in my pocket. And within the distance here now, how you'll be able to tell I do have explosive material inside of my pocket? You say, well, I can have a dog. Dog too far distance here is difficult. So any other method? So far, we don't have any other method. Especially within 100 meters away, okay? Now, we are able to develop a method to sensing 100 meters away now. 116 meters we demonstrated. So this actually is chemical biological signature here now. Perhaps one of the earliest terahertz wave imaging was really in 1995 by Bingbing Hu. Bingbing Hu was a student at Dave Austin's group. I was a research scientist at Columbia University. So once he left our group, he joined Bell Lab, and he imaging with terahertz wave, imaging a tree leaves. So you can see tree leaves, fresh tree leaves, and after a few days, after 2 days, you'll see all the vein, because the water evaporated, you have a much less absorption of terahertz wave through the leaves compared with this one here. This actual paper is one of the earliest paper talk about terahertz of imaging. Then later on, we built other real-time imaging rather than scanning. This imaging is pretty easy, come up from the detection part. Perhaps you have a two-dimensional terahertz pattern you like to imaging, XY distribution. You want to build a camera. Many years ago, there was no terahertz camera available. So we can have our visible camera here now. But how will we be able to see terahertz signal? So we have to use a visible beam as well. So I combine the visible beam, too big XY visible beam, overlap with the terahertz beam imaging, go through a large crystal. The crystal has to be large, okay, centimeter, not a millimeter, centimeter, even inch by diameter. So the terahertz imaging will change the spatial and the temporal distribution of index of refraction inside of the crystal, using an optical beam to redisplay the spatial and the temporal distribution. Then using an optical camera, CCD, to redisplay. Even we are not able to develop a terahertz camera during that time, you need multi-million dollars to do it. I don't have it. So we are able to use an inexpensive way to displace optical beam to do it. So actually, I test more than 20 different countries' currency. And first one is renminbi from mainland China, US dollars, and I have a euro, and I have a German money. Actually, do I have euro? I don't have euro during that time, probably. I have a pound, Singapore dollars, and also Korean here. And you know this currency here, if you have one, you have called watermark. Watermark is a intensity modulation in visible beam. That's why you can see a watermark. But a watermark also shows a different phase imaging. The light travels through different part of the watermark using different speed. The speed of the light travels through different part of the watermark are different. So therefore, not only phase shift, it also presents a phase shift because it uses a different time. By tracking the time of your terahertz wave through different part of watermark, you can identify what it is. Believe it or not, I got pretty good money from US government to use this money to track the suitcase money. They want to know is really a novel, a book, or maybe a bunch of the money. Hopefully they can track the money for the money laundering. Canadian company, I didn't show here, they contracted me to develop a method for the government and to identify those 16 methods for anti-counterfeiting in the bill. So Canadian company want to do that. So they asked me how much I will charge them to bill for the service we provide. University professor, it's hard to do that. So I scratched my head a little bit. I said, for you, free, as long as I can keep the sample. Sample is more money than which you can get a contract. So the time, actually, the imaging which I show you here, there was a CW imaging, there was time of flight imaging. This one shows the time of flight. So by a quarter, or by a coin here now, sending a terahertz wave imaging here. Time of flight, the time come to sample and coming back to you are different. So you can also track like a topology, like a depth information, give you tomographic information as well. One interesting thing is teapot. This is my teapot in my office. And half fill and full. No water here now. No water, terahertz wave goes through right away. With the water here, strong absorption. So you see them clearly. But that's probably not the way which you should know how many teeth in your pot. And I have a racquetball player in my office. Actually, I never use it. Visible beam. And this is actually 0.6 terahertz of imaging. So terahertz imaging here, see clearly what happened inside of your bag. Now, if you clearly see it, actually you're even able to see the word here now, because I believe there's different absorption layers compared with the lag which you package here now. How about shoes? Some of you travel, especially in US, require you to remove your shoes. Okay, not very happy, cold weather and the dirty floor. I was hoping to develop a terahertz wave imaging to image your shoes without taking it out. So this actually is my shoes. Not this one, which I wear now. Linear scale, and also log scale. And we are able to see something inside and hopefully provide spectroscopy information. I worked on this project for 2 years. Later, I gave up. The reason here, ladies have so many different kinds of shoes. And the ladies' shoes also have a metal inside to support it. And the metal will scatter, block, and terahertz wave. And imagine here now, I don't know how many shoes you have at your home. Here, my wife, she has a lot. And all the shoes she provides us, and we always get a very depressed result. Men's shoes works fine. Ladies' shoes, no chance. But something big is fine now. Actually, one of the earlier days, I used my briefcase, leather briefcase. I couldn't believe my students find a big knife, this big, and put into this big bag here now. So you see very clearly inside what happened, layer by layers, right? So it works pretty well. Then we continue to develop. This everything I mentioned is big size now. Scientifically, we are going to small. How small it is? 1 terahertz in frequency, in wavelength is a 300 micron. 300 micron is 1/3 of a millimeter. Our goal is sub-micron, or even better. I actually worked for 10 years. I got a 2 nanometer resolution using 1 terahertz wave. A brick record, we opened a couple Xiangpings already. But this one, I want to show you called terahertz dynamic imaging. Perhaps it's interesting in physics student. So the challenge is the terahertz wave, which we generate from an electro-optical crystal. There's a femtosecond laser. You generate a terahertz wave. And terahertz wave is a very long wavelength. It's a 300 micron. How you are able to imaging something much smaller than the wavelength? You can say, well, near field, right? Near field microscope here, you can do that. But can you do it at a little bit far field? So the idea is actually, if we're using part of optical beam excited on a piece of a semiconductor, we create a dynamic aperture. Perhaps we can improve our resolution. And this part is a electro-optical sampling system which I developed in 1995. And this is a dynamic imaging part which I'm talking about. So the concept is, terahertz wave spot is big. At least 300 micron for 1 terahertz, so huge, 300 micron, 3 times of your hair thickness. But optical beam can be 1 micron. You can focus your visible beam down to 1 micron. So the optical beam can be very small. We overlap terahertz wave and optical beam into a piece of a semiconductor. We let optical beam create free carriers. And once you create free carrier, you have a lot of free electron. Electron will screen, will block your terahertz wave. So basically, your terahertz wave before is this big on the semiconductor, but this tiny spot, very small spot, is blocked by the laser focus beam generating electron. Because of this, you can perform imaging much, much better than the wavelength scale of terahertz wave. So we try them here down to 22 micron, it should be micron here now, and all the way here. So we are able to imaging at a much, much smaller one. Conventional terahertz imaging here, see nothing here. Basically, you see some shadow here now. With the dynamic imaging here now, we see much clearer features of this one. So this is one way to show how to imaging something at a very, very small scale. We also developed a terahertz wave microscope. So I learned something from formal Bell Labs earlier work. But the concept here is a terahertz wave microscope, which I come up from here. This is a laser beam. Femtosecond laser beam go to a microscope objective, create a terahertz wave through an electro-optic crystal. Then I lay off the thin tissues on the top, then be able to measure T-rays. So this is in transmission, and this one is in the reflection. This one is in the transmission geometry. This one is in the reflection geometry. Coming in and reflect out. And we are able to provide a better than the millimeter resolution. So here's an onion cell. The big onion cell can be a few hundred micron long and a few micron length. Standard optical imaging, you see the onion cells. This is 1.6 millimeter diameter. 1.6 is pretty small. In the transmitted terahertz wave here, we are able to resolve each individual onion cells now. This again in the 1.6 millimeter diameter, the size now. We are really hope to imaging individual cells for others. Another thing which I'm very happy to report here is a CT. Many of you are probably familiar about CT or in hospital doing CT. One of my visiting students from Australia, he spent some time in my group, 2 years. He said, Professor Zhang, why don't we use a terahertz wave we call T-ray during that time to replace, or not to call replace, to something like X-ray CT, but using T-ray. So the concept here is actually using a T-ray or a terahertz wave through the material. Then you measure the distribution of your terahertz signal versus the rotation of the sample theta, as well as a translation displacement t. So this is a t, the rotation is theta. So you measure the power as a function of field as a function of theta and t. So then you use a Rodin transform here now. By measuring this p as a function of theta t, you are able to back calculate your x, y function here now. So that's actually we call T-ray computed tomography. And the students, visiting students is a Ferguson, outstanding student. So here's actually a sample, one of the earliest sample here. Just put the two plastic, make them S-shape, this S-shape, then you set the T-ray here, you rotate. And then by measuring the transmitted wave, you're able to get this sonogram. And sonogram is able to completely reconstruct the imaging which you will see it. It works pretty well. That was actually turkey bone from our Thanksgiving leftover. And then we're able to see through the power structure inside. Also a golf ball here now, we'll see what happened inside. Ping pong ball, we'll be able to see what happened inside. And also we are able to see a co-functional imaging to resolve the index of reflection change as small as a 0.001. What that means? The index of refraction of a very tiny change, you're able to identify it. It perhaps means the cancer tissue. Cancer's tissue and the normal tissue has a much, much bigger index of refraction change. But the difficulty is, most of the cancer and the normal tissue, they have a blood, they have a body liquid, they block terahertz wave. But if we can figure a way here now, this is called functional imaging and provide CT. This is actually air freshener, and some family using air freshener and sending a CT, terahertz CT here, you're able to see whatever left over inside of the plastic container. Now, next a few slides here, I'd like to show you something kind of different, but it's fun. Compare with a visible conventional lens versus a Fresnel lens. Conventional lens, right, you use every day, maybe even your eye using a lens. So you send a frequency here now, which is mu, you focus them down to a distance. You satisfy the law of refraction. This is a conventional lens. Some of you probably know there's a called Fresnel lens, okay? Fresnel lens, the Fresnel zoom plate. It acts as a terahertz lens. Now, if you have two different frequencies here now, mu1, mu2, suppose one frequency is twice as the other one, then this Fresnel lens will focus your two different colors at two different locations. Okay, so one is focal length is twice as the other one. So the focal length in Fresnel equation here, they satisfy the focal length is proportional to the wavelength you are using. So that's the key. That's important. So Fresnel zoom plate operate on diffraction or interference rather than the law of refraction. So now, for example, like this, conventional imaging. You send your optical beam here now. You have a conventional lens. Then you image this target from Z to Z prime, satisfy imaging equation, 1 over Z plus 1 over Z prime equals 1 over F. That's a conventional way. But what happens if you have a Fresnel lens, you know? Now you have a two color frequency coming in. So one color frequency can image the target at this location. The other wavelength imaging another target at different location, but both of them can be displayed them in the same imaging plane. Another way here, different location here will be imaged in the same location here. So that's the trick. Look what happened. This actually is an imaging lens which we built together with a New Zealand group. It's a silicon and make 8 layers. So this silicon is 8 layers, like a step, 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 then come back, step, 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 step here. It shows us this 8 layers imaging here now. So we use this one, we test the focusing capability first. Here's 3 different lenses. One is 2 layers, called binary layers. One is 4 layers. One is 8 layers of the zoom. Then focus terahertz wave. This is a focus terahertz wave by using 2 lenses. It acts as a lens. It's a plate, but it acts as a lens. So it's have an imaging here, 4 layers, 8 layers, much better clean. And also it's 1 order is better than 2 layers. So 8 layers, 1 order is better than 2 layers. We also prove the focal length is linearly proportional to the frequency you are using. The theory and experiments fit fairly well. So this is a key part. Now we're sending a terahertz wave coming in. We have a target along the terahertz beam path, 3 different targets. Our goal is imaging all 3 targets on the same imaging plane, imaging sensor here, 3 different targets, okay? We beam coming here, we overlap all 3 different targets on the same plane, and we need to identify 3 different layers, 3 different planes. So the imaging 3 centimeter away at 0.75 terahertz, we found this inverted imaging, this one. 7 centimeter away, we put another imaging here now, inverted terahertz wave imaging, we got this one, but it has to be 1.24 terahertz. 14 centimeter away, we have another target here now. We have a terahertz inverted imaging, but using 1.57 terahertz. Now, we are able to put all 3 imaging on the same imaging plane, but using different frequency, we are able to identify all different targets. That was really outstanding, interesting. You put all the image in the same imaging plane. By cracking the frequency, you are able to pick every frequency, and each frequency corresponding location along the axis. That's how you're able to identify this target, this target, this target on the same imaging plane using different frequency along terahertz frequency range. So here actually is another one here, one of my postdocs. She was carrying the system here to, in Mongolia, a wall painting, using terahertz wave see through the wall. And they are able to identify a number of missing parts. And another one here actually was really a painting here in temporal panel. This is in Italy here. And the latest one, which I'm a little bit scared, is actually they measure a bird mummy. And they use terahertz X-ray to see something here now, but they found using terahertz wave, they see some features which conventional X-ray is unable to identify. So my postdoc, Bianca Jackson, she used to be a postdoc for Jura Moreau to develop a 5 CPM laser. So now she's actually developed this system. Well, as I said before here now, the most important products we have, student. And I graduated 28 PhD students. This is the group which I graduated. The last group I graduated when I was at RPI. A lot of beautiful ladies here now, dressed nicely. Yeah. I think I still have a few minutes, so I'd like to very briefly report a few things very new. One thing is very new is people say, well, you're talking about terahertz wave. You use a so expensive system. Yes, I'm very well supported. I have $40 million research funding. $40 million research funding. I couldn't use all the money. At the end of each year, I have to figure a way how to how to spend the money. Now, but people say, well, how can I do terahertz research without a big budget? There's an easy way. Look at this. Microscope objective. Focus a laser beam. Focus to a very, very small spot. This tiny spot, your eye looks big, but actually it's micron size. It shows a fluorescence. You focus your optical beam by a microscope objective. You create a very tiny air plasma. This air plasma radiates the terahertz wave. Not in the forward direction, in the sideway. Why? When you use a laser beam focus air here now, you create air plasma. It has upon the motive force to have a distribution between electron and ionized material. So you artificially create a dipole along this axis. For physics students, you know, electromagnetic radiation from dipole never radiate along dipole axis. So if your dipole created this way here, it might be radiated sideways, right? This is what we believe, so we measure it. So my students actually published a paper in Optica terahertz emission from laser-induced microplasma in ambient air. Some of you probably know I'm the editor-in-chief of optical letters. I have 60 editors in my team. And as an editor-in-chief 3 years ago, I announced I do not publish my own papers in optical letters to avoid conflict of interest. Some of you, if you submit a paper to optical letters, has been accepted, you're happy. But if has been rejected, which we have only 30 plus acceptance rate, you'll be unhappy. If you're unhappy, you say, well, Dr. Zhang, he published his own crappy paper in this journal. I don't want to get in trouble. So I decided not to publish my own paper in this journal as long as I'm editor-in-chief. But I'm able to publish other journals in OSA journals. Optica is a great journal, which I highly recommend it. So we have paper in this place. So the idea is, one use a regular lens, using intense laser, you create air plasma, not plasma, air plasma, not a microplasma, very long plasma. You create a channel called filamentation. And this filamentation can radiate terahertz wave. If you use a shorter focal length, you make them smaller, and the radiation actually becomes sideways. If you use microscope objective, which use much less energy, because you focus your beam to a small spot, it radiates sideways. So this is the concept, this is a simulation. Here's measurements. We send the optical beam, which is a nanojoule optical pulse energy here now. We focus the plasma. And this plasma radiates terahertz wave, radiated around 80 to 90 degrees. Have no radiation in a forward direction, but radiate sideways. So this plot here shows the angle, forward, perpendicular, degree, and the color shows the intensity of the terahertz field. So most radiation radiates sideways. So it works. Great. We're very happy about it. And we found the radiation around 80 degrees sideways when you use a 65 microjoule. While you use a sub-microjoule, of course, signal become much weaker, but you still get a terahertz wave radiated out, So this is a cheap way to get a very intense, not very intense, get terahertz wave now. Now, another two things which I like to share with you here about imaging. I was hoping to share with a terahertz imaging. I assume probably not a lot of people understand the terahertz quantum imaging. The terahertz quantum imaging means using one photon, generate two photons. And one photon is terahertz photon. One photon is a little bit less than the input optical photon energy. Now using terahertz photon to image material, to see you, but not detect. Using optical beam to detect but not see you. This concept was come up a little bit over 2 years ago when I hear Anton Zeilinger from Vienna. He was talking about two different wavelengths to do quantum imaging. So when I hear his talk, I went to the patio to ask him, and he says, great idea. So the terahertz wave will see you but not detect. Optical beam detect but not see you. We're not there yet. We should be able to construct terahertz wave imaging by measuring optical beam only. This is a project I started 3 years already, and we're still working here. I don't have some results to present to you. This is one thing. But it's really, we're revolutionary our concept of imaging using a you can see that coherence using this called entanglement. This is one way. You don't have to use entanglement, I was told, called classical ghost imaging. But using entanglement, So two photons entangled together. We have no idea how to measure terahertz photon and the visible photon entanglement. We have no idea how to do it now. I hope I do, I don't. But even not, I do believe sooner or later, maybe not more than a year, we should be able to present results of terahertz quantum imaging. We are very close now. We have all set up ready, and we just need to take some time. It's number one. The second thing which I make an announcement, I don't want to show you here today because it's not fair for my student. I have a big mouth, okay? I never keep secret. That's my problem. Spent more than 10 years now. We are finally solid, demonstrate we are able to generate intense terahertz wave from liquid water. So people not in terahertz community, you don't know how important it is. Water is considered as an enemy of terahertz wave because absorption is so high, so high. And I even don't believe myself now. I put this target here many years ago, 10 years ago, is because I trust Einstein. For physics students, you learn A and B coefficient. You know Einstein relation. A and B are coefficient. One is emission, one is absorption. Absorption and emission, they are related. For some material, like water, has a very strong absorption. Perhaps we should study their emission property. Liquid water have a very strong absorption, but no one really studied using liquid water as a terahertz source. As far as I know, nobody do it. Because it's so obvious, it's not a good project. No one want to do it. I didn't give up. The reason why I didn't give up, I have a stupid concept. How stupid it is. I said, if you do it, you may not get it. But if you don't do it, you guarantee don't get it. So I have this philosophy. So 10 years ago, I talked to my students and said, look, how will we be able to generate a terahertz wave from liquid water? We tried many different methods, many different methods. And no one really carried on more than 1 year. Until I get students, join my group. New students have no fear. Give the difficult project to the newer student. They don't know how difficult it is. So he worked for 8 months. And he was depressed. He wanted to give up. But he thought, I will try 2 more days. 2 more days. He did. 2 more days, he thought he may see something. He came to me. I tried for 10 years, never get it. How can I trust for this? I wasn't believe that one. But actually, I thought maybe you should do a few things to verify. Because water absorbs so strong, it's so difficult for terahertz wave to get out from water. How will you be able to prove? We designed very clever way to do it. I think finally, I'm going to announce this one, a major observation in Cancun, Mexico, for our IR millimeter wave. Perhaps that will be the first experimental demonstration to generate intense terahertz wave from liquid water. So that would be, for me, scientifically, was impossible before. Hey, we make it happen. So very proud of it. And I did open a bottle of champagne, celebrate with all my students. So that's probably the end of my talk, really facing to our student here now. And as I said, students are our best product at the faculty here now. Your successful is our successful. I wish all your good luck for your career, family, find a dream boyfriend, girlfriend, and start your life happily. Thank you very much.
Thank you. I think already all of you know how to get good motivation for science now, but perhaps you know want to know something more from this. We have some questions. Oops.
What is the fundamental mechanisms behind the absorption of terahertz waves?
The question is, what is fundamental mechanism behind the terahertz wave absorption? Terahertz absorption by different material may have a different mechanism. For example, water, let's say water vapor or liquid water. Water vapor, they have some kind of resonance level. Water is a polar molecule, so they have a stretching mode or vibrational mode. They are happy in terahertz or middle infrared frequency. So that kind of energy resonance will resonantly absorb the incoming terahertz wave. Okay. Solid state material like semiconductor, gallium arsenide, zinc telluride, indium timonide, they have a called collective mode of the phonon, optical phonon. Phonon also have absorption of terahertz wave as well. And this is actually absorption. Besides of absorption, they are reflection, scattering as well. Terahertz frequency is a range sub-millimeter wave, so there are a lot of scattering if you send the terahertz wave through a porous material as well.
I have a short question. You showed half-full teapot imaging, and was it a hot tea or a cold tea?
That's actually a very interesting question. I never thought about it before.
It was hot at the beginning.
Yeah, actually you can get a thermal imaging for temperature as well. For our measurements here, we just show the water level of that one here now, so we are unable to tell the temperature of that teapot. We're not really.
How long took this measurement?
For this measurement, it can take an hour, but the other measurements can take a millisecond. Now we'll be able to do a millisecond. The most expensive machine I ever built in my life is a build a machine to count money. Remember, actually, if you are, I don't know, you use euro or using your money here, you have to use manpower to count the money sometimes in the bank. They use a machine now, right? But even using a machine, they still recount it. I built one of the most accurate machine, count your money at the speed of the light. It can count entire US debt in a couple of seconds. We have $1 trillion debt in a couple of seconds. How we did it? Each currency has certain thickness. You know the index of refraction. You count the time to travel through each bills, then you can calculate. That's why you count your money at the speed of the light. But it is the most expensive machine. And probably even US government is not willing to use it to count their money.
Could you keep the samples?
I wish I could keep more samples.
One more question about the source of Terahertz waves in an experiment with different Fresnel lens. What kind of source did you use in this experiment? Because it's above terahertz. It's not gamma diode assembly, yes?
Okay, the question is about the radiation source for my Fresnel lens.
Yes.
I use different gun diode. I did use different gun diode. The gun diode is 200 gigahertz, 400 gigahertz, 600 gigahertz. I have all this kind of 100 gigahertz as well, all different kind of gun diode. You also can use a broadband terahertz wave. But we don't want to use too broadband because they overlap too much. So we prefer individual either gun diode. There was another called BWO, back wave oscillator, which is sold by Russia. Now US maybe make them as well. It's another way can provide narrow band CW terahertz wave. So we use that one.
As far as I understood, in order to increase your resolution, you used light spots in the center of your terahertz. Yes?
You're talking about dynamic imaging.
Yeah.
Dynamic imaging, we create a block spot using optical laser beam to create a carrier. block terahertz wave, yes.
So why did you use light to block terahertz wave instead of, I don't know, some kind of piece of metal maybe?
Yes, you can. You can use some really solid target. The reason why we use optical beam, because optical beam can be modulated. We can, using a mechanical chopper, to chop optical beam, so that we block the terahertz spot here can be on, off at optical chopping frequency, typical kilohertz. Then we measure the transmitted terahertz wave using a lock-in amplifier. So we'll be able to measure very small change, 10 to the minus 7 change of the entire beam propagation transmission quality. That can provide very, very good resolution and sensitivity. Yes, you can do that. You can put a metal here, but you want to dynamically change. So in general, it's very difficult to do it. In principle, it is.
Your lock-in is very good, minus 10 to the minus 7.
Typical lock-in amplifier can measure transmission change, delta R over R or delta T over T, between 10 to the minus 7 to 10 to the minus 8.
No more questions? Then let's think again.
Thank you.